general loading, shear, and moment relationship. For any beam with distributed loads, we can establish certain general relationship which will be aid greatly in the determination of the shear and moment distribution along the beam. For this purpose, consider this picture. Consider this picture. Represent a portion of loaded beam where an element of the beam isolated element of the beam isolated with dx with the loading W omega represents the force per unit of the distributed force. At the location X, the shear V and the moment M acting on the element are shown their positive direction at each point. On the opposite side of the element, where the coordinate is x plus dx, this point, these quantities are also shown in their positive direction. They must, however, labeled v plus dv and m plus dm. The applied loading omega may be considered constant over the length of the element, since this length is a differential quantity and the effect of any change in omega disappears in the limit compared with the effect of W omega itself. Equilibrium of the element requires that V as a positive, in the positive direction, minus omega dx minus V plus dV equals to 0. Now we can obtain omega dV on dx. We see that from this picture we see that from this equation that the slope of shear diagram must everywhere be equal to the negative of the value of applied loading. These equations holds on either side of concentrated load but not at the concentrated load because of the discontinuity produced by the abrupt change in shear. We may now express the shear force P in terms of the loading omega by the integration as this relation of V with dV x omega dx V minus V0 dx. Or we can write V equals to V0 plus negative of the area under the loaded curve from is negative of the area under the loading curve from x0 to x. In this expression, V0 is the shear force at x0 and V is the shear force at x. Summing the area under the loading curve is usually a simple way to construct the shear force diagram. The equilibrium of the element shown here requires also another relation for the moment equilibrium relation. Summing moment for the left side and positive clockwise, we have this relation M. V produce no, but W omega can be produced some multiply to dx, the distance to the left side, V plus dV dx M plus dN. The relation is M plus W dx V dx plus V dV dx minus M minus dN. Higher order terms can be eliminated. So the final expression is V dx equals to dm, V equals to dm on dx, or m minus m0 equals to integration m equals to area under the shear diagram from x0 to x. In this expression, m0 is the bending moment at x0 bending moment at x. For beams where there is no external Ternally applies moment m0 at x0, the total moment at any section equals to the area under the shear diagram of that section. Summing the area under the shear diagram is usually the simplest way to construct the momentum diagram. When v passes through 0 and is a continuous function of x with dv when v the bending moment will be at a maximum or minimum. We have now two relations that said that v equals to omega on dx and v dm on dx. dv on dx d2m on dx2 If omega is a known function of x, the moment m can be obtained by the two integration, provided that the limit of integration are properly evaluated each time. This method is usable only if omega is continuous function of x. When bending is in a beam occurs in more than a single plane, we may perform a separate analysis in each plane and combine the result vectorially.